thank you very much, guys, for the super nice invitation. So I'm happy, super happy to be here. And yeah, but you guys gave me a kind of problem. Sorry, can I erase this? And this? Carla. Mejor no? Okay. Okay. Okay, so I'm supposed to talk about beyond WIMPs, so kind of advanced topics on dark matter. However, it was kind of complicated because of someone, I will not say her name, because someone is covering basically everything, right? So someone is talking about, look, primordial black holes, cold dark matter, work dark matter. This is Planckian interacting dark matter, double disk dark matter, self-interacting dark matter, mirror charge dark matter, blah, 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 blah. So basically everything. So I don't know what I'm doing here. So it was quite a challenge to decide exactly what to present. So that was everything. Thanks. Yes, questions? So if I want to talk about beyond WIMPs, it's better to start discussing about WIMPs. So originally, I was expecting someone to discuss about WIMPs, the Boltzmann equation. My notes, sorry. But it was not covered this morning, and it kind of makes sense, right? So the first lecture is supposed to be about the motivations, the conditions that viable dark matter has to fulfill. So first, I will very fast discuss about WIMPs before Graciela discuss that. So revenge. Okay. So the idea of this, okay, when talking today and tomorrow, the idea today is discuss more about alternatives from the particles physics front, and tomorrow will be more about cosmology, right? So if we want to discuss, to keep track, okay, the question is how dark matter was produced in the early universe. So if we want to understand how, so the dark matter genesis in the early universe, there are two ingredients. So really the particle physics, so you can think about a particular model, so supersymmetry, extra dimensions, singlet scalar dark matter, ALPS, fuzzy dark matter, right? So there are these really like particle physics mechanism. But also the other front is really cosmology, right? We have to have all the cosmological evolution of the universe under control, and Graciela emphasized this point this morning. So today, the idea is to focus on one of these mechanisms, or one of these kind of mechanisms for producing dark matter from the particle physics point of view, and tomorrow is to discuss more the cosmology, right? The parts of this standard cosmology, early matter dominations, what happens if we have primordial black holes, all these, and reheating. So the possibility of having a low temperature reheating. So that's that's for tomorrow. So first thing, before discussing the beyond WIMPs, will be a couple of words about WIMPs. So really, we will not discuss about particular models, so supersymmetry, neutralino, blah, blah, but more about general paradigms, general mechanisms for producing this dark matter, right? So WIMPs correspond to the weakly interacting massive particles, right? So weakly doesn't mean electroweak. It could be electroweak, but I mean not sizable. It's like not super strongly interacting dark matter, right? So, but it doesn't. It's not electroweak in particular. So the idea of WIMP is we have equilibrium. So we have like we have the standard model, right? In the early universe, we have like this plasma of standard model particles, and we can also have dark matter particles, so these two sectors, and we want them to interact. We want them to reach equilibrium. We want them to reach both chemical and kinetic equilibrium. So if you think we can have both elastic and inelastic interactions between, imagine, two gases, right? So we can have interaction, okay, we can reach equilibrium, in particular chemical equilibrium, if we have, for instance, a couple of dark matter particles that annihilate into a couple of standard model particles, whatever, E plus, E minus, a couple of Higgses, quarks. So we want this reaction, this number changing reaction to happen. So annihilation of dark matter, I want the opposite. So creation, so annihilation of standard model into dark matter particles. And we want these two reactions to happen. So let me put the two arrows. So this size and this size. The two reactions to happen exactly at the same rate, right? If these reactions happen at the same rate, that means they reach chemical equilibrium. And that's the idea of WIMPs. If you understand that's it for WIMPs. So now let's go beyond WIMPs. No, I'm kidding. So the idea is to track the dark matter number density. Yes? Sorry, what's the question? Is there a diagram related to that process? Yes. Yeah, okay, the point is that I don't want, I will discuss some models, but for now, let's assume that this reaction happened. You can imagine that you have a mediator, heavy, light, maybe you have a contact interaction, so no mediator. We don't know. At this point, we're completely agnostic. We don't care. We just want this reaction to happen and to be in equilibrium. Yes, thanks. So please interrupt me. No need to wait until the very end. Okay, so this reaction happened. You can compute in a given particle physics scenario, the Feynman diagram. You can compute everything, loop, blah, 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 all that. But at this point, it's not needed. So this reaction happened at the same rate. Equilibrium, chemical equilibrium is reached. So we want to compute this number density of the dark matter particles. And number density is basically the number of dark matter particles over the volume, right? Over a given volume. So this basically, yes, that's it. We want to keep track of the evolution of this guy because we want to compute the relic abundance. And we have seen that this is basically 25%, no? At present, it's 25%. So what we want to do is to have a model, a particle physics model, that fits the observations. So what we want to do is to compute the evolution of this guy. So the time evolution of this guy. And of course, okay, remember, this is number density over a volume. So it will change if I change the number of particles, right? If there are number changing reactions, but also if the volume is changing, and we know that the volume changes, right? The universe is expanding. So there will be a term, we can compute this formally, the Liouville operator. So it will be a term that keeps track of the evolution of the expansion of the universe. And it will be something like this. I mean, of course, we can compute everything this from first principles. Okay, so N, remember, is number density of particles. H is Hubble expansion rate. So it's not the Hubble parameter at present, but it's really a time-dependent quantity. It's how is the universe expanding. This 3 is very important, means that the universe has 3 dimensions in space. So this term keeps track of the evolution of the volume. So in particular, we have to make some assumption about how H evolved, what's the evolution of H, what's the energy content of the universe, what's the Hubble expansion rate. And I think with Graciela, she will give you, Graciela, much more details. So, yes. Are you judging my scripts? Yes, sigma V. Sorry. So maybe this, okay, once you have a particle physics, so you can compute this, right? This is basically, this is a thermally average annihilation cross-section. It's something that depends on the temperature. So here's all the particle physics is here. So when you have a fixed particle physics model, you can compute that. So it's basically a cross-section, right? The cross-section depends on the energy density, S parameter, right? And the center of mass energy density. However, you're in a thermal bath, right? So you have to take a thermal average just because you have a thermal distribution, right? So I don't know, the important thing is not the details, just the general idea of this. So here is basically all the information of all the reactions and change number density. So inelastic interactions, and this you can compute. Once you fix your dark matter model. N squared, the same, and N equilibrium. Once, I mean, if this is fixed by the statistic, this could be Maxwell-Boltzmann, Fermi-Dirac, depending on the spin of your dark matter particle. So again, this you can construct from first principle, but here just presenting to you. Maybe I hope it's not the first time. So this could be solved basically analytically or numerically, right? And I can give you some ideas here. So here, for instance, but even if that's what you want to do, it technically makes more sense to make just a change of variables. So let me define this capital Y, this comoving number density of N over S, right? Number density over the entropy density. And why the entropy density? The idea is that if there's no interactions, N, remember, is number density, is number of particles over the volume. The volume is increasing. So N, the number density will decrease just because of the expansion of the universe. However, if I define these kind of quantities, I mean, this S, this entropy density, will also scale like the same shape of the wave of N. That means that this guy, this capital Y, this comoving number density is something that will be constant if there are no interactions. And why? Because both N and S will scale like 1 over A cubed and 1 over A cubed. So at the end, this is something that is supposed to be constant. It's an object that by construction is constant if there's no interaction in the case where the entropy density is conserved in the case of adiabatic, and that's what we are assuming, right? We will assume for now, today, that we have some adiabatic interaction so that the entropy, is conserved. So I can just make a change of variable. Instead of talking about N, I keep track of the comoving number density, and I can define X like the mass over the temperature of the photons. Yes? So X goes like 1 over T, so it's basically a proxy of time, more or less. So the universe expands, the temperature drops, and therefore X increases. So if I can assume a couple of things about the evolution of the universe, so in particular, if I assume that I'm in like what is called the standard cosmology, meaning that if Hubble is dominated by radiation, by standard model radiation, and if I assume, so I'm assuming radiation domination means that Hubble is dominated by standard model radiation. If I am assume that standard model entropy is conserved, I can solve this equation, right? And have something like this. So I hope that this is not the first time that you guys are seeing this. Anyway, I can give you some details. So here I'm showing you the evolution of this number density, this comoving number density, exactly this parameter here, as a function of X. So time is flowing from left to right, so temperature decreases, X increases. Here, this blue line corresponds to the equilibrium. So suppose we want a fermionic dark matter, will just be the Fermi-Dirac distribution, right? Number density at equilibrium. And the point here, remember, we're saying that we have a WIMP, so that this reaction is in equilibrium. So we expect this dark matter particle to track equilibrium, and that's exactly what we are seeing here. So the thick black line is the solution of this equation, the typical solution of WIMPs. So dark matter is tracking the equilibrium, and at some point, this equilibrium is broken due to the expansion of the universe. So if you want, dark matter still wants to meet, but however the universe is too large, is not hot enough, is very diluted. So this interaction, even if it in principle could take place, they will not, because if you want the luminosity, if you think in terms of collider, even the cross-section is big, the luminosity is small, so number of interactions is basically none. So you have less than one annihilation per Hubble time. So at some point you go out of equilibrium exactly as that, so dark matter does not meeting anymore. This reaction is not in equilibrium anymore. And this guy, you reach a plateau. And why a plateau? Because by construction, if there are not annihilations, you expect this guy to find a flat asymptotic solution. And that's basically the idea of WIMPs. So WIMPs in five minutes. Right? So yes, please. No.
So hi again.
Hey.
I mean, how do you know this stuff? I mean, it is not theoretical, or do you have any evidence of this to plot this graph?
For the equilibrium?
Yeah.
No, but the equilibrium, you know. I mean, you know that the partition function is basically 1 over E minus T over M plus or minus 1, blah, blah.
Okay, but you need the abundance of the dark matter to know when the universe is too big to not have this equilibrium, right? I mean, if the abundance is too much, the equilibrium will be broken in a different scales of the universe.
Right, so a different value of X, if you want, yes.
Yeah, so how do you know that? Or you don't?
A priori, you don't know.
Okay.
You can estimate it analytically or numerically, right? The only thing that you have to assume, of course, is, okay, yes, as a spin, a mass for dark matter, something about entropy, about Hubble expansion rate, and low particle physics, right?
Okay.
This typically, this is in principle a complicated function of temperature, right? And the couplings and masses. However, de facto, typically, what you care here is not the evolution, at the time evolution, but the value at a given moment, so the moment of the freeze out. So I think a good approximation, this, for you, for technical point of view, you could typically take as a number.
Ah, okay. And what's the omega, the capital omega?
Omega h squared, that is basically 25%.
Okay.
Yes, so if omega is the ratio of energy density in dark matter over the critical, so the universe is flat, the total, the critical, and h is the, how it's called, the reduced Hubble parameter, I think is 0.7, so 25.7 squared is 0.12.
So h is not the Planck?
No. It is
okay.
I think it's called the reduced Hubble parameter.
Okay.
It's a number, I think it's 0.7, something like this.
Okay.
The point is that this is basically 25%.
Thank you.
Yes, thanks. Okay, I have to hurry. Okay, so that's the idea. Okay, and two more comments. So typically for WIMPs, what you need is a freeze out, if you see there, of order, okay, two things. So this sigma V has to be of the order of 10 to the minus 26 cubic centimeter per second, which is basically picobarn scale. Yes, this is like 10 to the minus 9 GV minus 2 for you to have minus 2. An idea of this number at the moment of the freeze out. Freeze out means chemical freeze out. Yes. And for WIMPs, the X of the freeze out, so basically the dark matter mass over the temperature of freeze out, it has to be 20, 30, something like this. And you can see it here, more or less. So, I mean, it's not really something like very well defined, but you know that you have the departure of equilibrium more or less here, and this is basically X order 20, something like this. Okay, so that's the first thing. I want to emphasize that I'm talking again here about chemical interactions, so inelastic, number changing, violating. But there's another equilibrium that will be very important. Is the, okay, that's chemical. In the sense, in elastic, I don't have room anymore. In elastic, this is written in elastic. But if you have these interactions, you can just rotate it, right? And have elastic interaction, beer balls, huh? So dark matter plus standard model, that gives dark matter plus standard model, right? Really elastic interactions. So this is, I mean, we don't care about this kind of interaction for WIMPs, because this interaction, I mean, is elastic scattering. It's not changing the dark matter number density. I start with one dark matter and I finish with one dark matter. Okay, fine. But it's completely unsensitive. I mean, these processes are unsensitive because it's not changing the dark matter number density. However, this kind of process guarantees kinetic equilibrium, means that I will have like a redistribution of momenta. So that this kind of interaction, if there's an equilibrium, it will guarantee, okay, let me put this kinetic. This is elastic. And this will guarantee that the temperature of the photons of the standard model is the same as the temperature of dark matter. And this typically is broken much later, so I will call this xk. So meaning the moment, okay, mass, as usual, over tk, and this is the moment at which this kinetic equilibrium is broken. So the last moment which I can guarantee that the two temperatures are exactly the same. For WIMPs, I mean, this is huge. Huh? This could be, I don't know, 10 to the 3, 10 to the 5. It's a super large number. And we basically don't, for WIMP, we don't care about it because we just care about the final abundance. And this is, okay, it's fine. How is temperature evolves? Good. But for the relic abundance, we don't care about much about it. And last comment, I can make an, if I assume that you have an instantaneous decoupling of this guy, so it's following the equilibrium, and at some point it goes out of equilibrium. Just to emphasize, this is basically the y at the moment of freeze out, and this is basically x freeze out 3/2. Yeah. Just to emphasize that this guy is really given by the moment of the freeze out and have an exponential sensitivity due to the Boltzmann suppression of the non-relativistic dark matter particles. Good. You asked me about the dark matter model, so we'll just be super fast. There's one model. I will not give you more details. So you want to compute that. For instance, you can imagine that you have a singlet scalar that we'll call S. So dark matter will be this S that talks to the standard model just via the Higgs. Small h is the Higgs, right? So it can so the first diagram corresponds to a contact interaction before the electroweak phase transition. After the electroweak phase transition, you have the Higgs takes a wave. You can develop this kind of processes, and dark matter can communicate via the mediation of the Higgs with the standard model, so with the Higgses, with fermions, or with the gauge bosons. And you can compute that, for instance. So you compute these diagrams, you can compute the sigma v, you can do the evolution, and you can see what are the required coupling of these trilinear, or the quartic coupling, so the Higgs portal. So this coupling here, for instance, where it's Higgs and two dark matter, or two dark matter and two Higgses, right? Here, for instance. So typical plots of WIMPs, you have the dark matter in the ballpark of GVs or TVs, and you need couplings of order 1. 1, 10 to the minus 1, 10 to the minus 2. And okay, you have some features because of the kinematical thresholds, the Higgs funnel. Yeah, I mean, just to give you a taste about what WIMPs are. Yeah, sorry, I'm going super fast. Yes. No, it was just a choice because yes, I mean at this point because for me I think it's one of the easiest model. So we just add a scalar, with a symmetry because you want to protect, you want this particle to be completely stable. So you put a scalar, a Z2, for instance, and basta. Yes?
Why did we, is there a reason why you're starting the plot at 10, like at the GeV scale and not lower?
Yes. Look at the couplings. So I'm stopping here because I prefer couplings to be perturbative. So that typically puts a bound, a lower bound of GV and an upper bound at 100 TVs or so. So basically perturbativity.
And is that for always or for just like
So for WIMPs, if you demand unitarity, I think the bound is 130 or something like this, TVs.
Okay.
Yes. Again, assuming this thing, radiation domination, and conservation of entropy. Tomorrow we'll see a possibility of keeping the WIMPs, in particular, giving exactly this model, how to explore much higher masses and smaller couplings, for instance, within the WIMP paradigm, but playing now with cosmology. Yes, thanks. Yes. You're not allowed to ask, man.
For the second equation, you assume a Maxwell distribution, right?
This is the second
No,
equation?
the second.
This is the second?
Yeah. Do you assume a Maxwell distribution, right?
No. At this point, no.
No?
Here? No. For this point?
For the sigma B.
No. How to compute, that's another story. I didn't tell you how you compute this.
Okay.
But no, you can do with Maxwell, or you can take the full...
What happens if you assume another distribution, like a Fermi?
You can do it. I mean, you can even
anything?
assume a non-thermal distribution, some super complicated thing. I mean, how to compute it is another story.
Yeah.
But at this point, I'm completely skeptical about it. I mean, you can do any distribution.
Okay.
You can assume, for instance, that these two guys have different temperatures. Yeah.
Okay. How it change if you if it's a inelastic dark matter? Is you need to agree at the quantifications?
Yeah. Yes. I'm here assuming that you really have annihilation, but you can do the case, for instance, where you have semi-annihilations or co-annihilations.
Okay,
Yes,
okay.
right. The idea is very simple. For instance, the solution of the Boltzmann equation will be basically the same. So this thing will be basically the same for annihilation, for co-annihilation, for semi-annihilation, sorry. Because the idea at the end is the same. You're in equilibrium, and then you break equilibrium. So the fine detail will be different. However, the general picture remains the same. Yeah, of course, you have to make some small modification, and we will do now a small modification of this. And yeah, thanks. Okay, yes. WIMPs in 2 minutes. Now, so if I write beyond WIMPs, I mean, this is like infinite. So in the next 2 hours, I will talk about beyond WIMPs, but in the thermal side. Thermal dark matter. And why? Because I think it's like an order one modification. We will extend this, we will modify it it will be very simple modification. But the phenomenology and the parameter space favor will be very different. So the idea is that, remember that for WIMPs, the basic thing that we have equilibrium, we have 2 equilibrium, we have chemical, and we have a kinetic equilibrium. And in WIMPs, the hierarchy of breaking this is very clear. You first break chemical equilibrium, and then you break kinetic equilibrium. Yes, and the final abundance basically depends on the moment at which you break chemical equilibrium. So one small modification, maybe it's in what you had in mind, Javier, is change this reaction. So we can, because at the end, what we want is to take into account number-changing reactions, a reaction that change the number of dark matter particles. We're going from 2 to 0, right? So that works. We want to tune the abundance because we have measured it's 25%. We have to tune this number. How? With particle physics, like this. So we can imagine, for instance, reactions that change number density now within the dark sector. Here was in the visible sector, so dark sector and visible sector. We can imagine reactions that only happen in the dark sector. So for instance, you can imagine a reaction like this. 3 dark matter particles that give 2 dark matter particles. And these these reactions are in equilibrium, again, meaning that this reaction 3 to 2 and 2 to 3 happen at the same rate, right? And at some moment, this reaction will go out of equilibrium, right? And then, blah, blah, we will get, no, don't look, yes, something like this. And I put on purpose exactly the same plot because the phenomenology, I mean, if you solve, of course, we have to solve different Boltzmann equations. Let me write it for you. But it's basically the same thing. The evolution on time plus 3hn. This is the same. This is a universal term. This only giving information about how the universe expands. So this thing is exactly the same thing. So Liouville operator is the same. Collision operator will be different, but slightly different. So it's again a sigma v squared. It's a 3 to, this is not really a cross section. Interaction rate, right? Interaction rate is something more clear. N cube, because I have 3 guys, minus better, n squared, n equilibrium. N squared 2, and I have to put 1 equilibrium there for, well, I can give you the details afterwards. So just to motivate, to tell you that this reaction is different. The Boltzmann equation is different. However, if you solve this, it's something very similar. And why it's very similar is because it's the same idea, right? So when this reaction is very effective, when it happens more than once in the whole time, the dark matter is tracking the equilibrium exactly as before. And at some point, you break equilibrium, you go out of equilibrium, reach the plateau. So this is a asymptotic solution. Yes? No, the tuning, sorry, forget that. No, what I have in mind is that what you have to reproduce, you have to have a model that reproduces this 25%. I was not thinking about fine-tuning or something like this. No, not right. No, sorry. What I have in mind is that we have to reproduce, to feed observations, this 25%, and we do it by playing today with particle physics. So with this, with annihilation cross-section or whatever, these interactions. You're right, yes, but yeah, sorry. I should not have used this taboo word. Yes, okay, and this is kind of guaranteed if I have, exactly as in the case of WIMPs, this, I forgot to say, this is usually called SIMPs, meaning strongly interactive massive particles. W was weakly. S is strongly interactive massive particles, and that is basically the idea, is to have it's basically the same thing, but it's the freeze out in the dark sector, right? It's only dark sector particle here, only dark matter particles flowing here. Why strongly? I will see in a moment. Strongly or self-interacting, sometimes it's called self-interactive massive particles. And here I also want to have exactly the same hierarchy, meaning that I want the chemical equilibrium to be broken first, and then the kinetic one. So because I want this to happen at the same temperatures. So I want the T freeze out to be much higher than T kinetic, so that the T of the temperature of the photon to be the same as temperature of dark matter at the moment of the freeze out. Yeah? So again, so you want, you can have, for instance, I'm putting here 3 to 2, you can have 4 to 2, you can have 100 to 7, right? What I want is a reaction that violate the number density. So in elastic interactions, and that's a plot that now I want you to see. For instance, in exactly the same model that I showed you before, you will not have 3 to 2, because, or in general model, where they have like a Z2 symmetry, like neutralino dark matter, you have a parity that forbids this interaction with an odd number of particles. For instance, I have 5 particles. So in some, you can in some models, for instance, where you have like a Z2 symmetry, something like this, like maybe like in supersymmetry or in Kaluza-Klein, 3 to 2 reactions are forbidden. However, you can always have 4 to 2. So I'm just giving an example of 4 to 2, just to emphasize that several things. See, if S is dark matter, here the only particles flowing are dark matter. There's no standard model at all, right? It's only S and only quartic interactions between the dark matter, right? Only quartic interactions, quartic, and quartic, right? So these guys, for instance, I can compute, and I did for you, so you will be very happy to see, for instance, this sigma v cube interaction rates, forget. So it will be, I don't know even what I'm writing this for you. So it will be just a coupling that I call Y is the quartic coupling over M power 5. Just to give you an idea of what are these kind of, it's not, I don't even know how to call these generalized cross sections or whatever, right? These reactions 4 to 2. Actually, this is 3 to 2. I'm just, yeah. 3 to 2. And you can do the same exercise as before. This one. For instance, okay, this is a very crowded plot. So forget about basically all the information. I'm just showing you the mass, the typical dark matter mass in MEV. So it's a different ballpark. It's lighter than in case of WIMPs as a function of the quartic coupling, right? So really the self-coupling. And I just want you to see this line, right? So if you're on top of this line, you're fitting the observations, right? The 25% dark matter observed. So what you need, again, is to go to the MEV ballpark, right? So you need kind of light with respect to what is expected for WIMP, so sub-GV dark matter. And this lambda is a quartic coupling, so couplings within the dark sector, which are sizable enough. So this is typically called SIM, so strongly interactive massive particle. So of course, nothing to be, no relation with QCD, or self-interacting, maybe it makes more self-interacting dark matter particles. Yes?
The same question I did this morning. How we can know experimentally that this is happening? Because it's, okay, it can happen, but how we can prove it?
Yes, I will have some comments at the very end. I can give you some, here you can see, I already have an idea. So the mechanism is completely different. First, the masses is, I mean, if you find a mass of, dark matter of the MEV ballpark, it's unlikely to be a WIMP, right? In the same sense, if you find that dark matter is TV, SIMS is super disfavored, at least within the blah, blah. Here also the couplings are different. However, remember that I assume that the kinetic equilibrium, I want to have kinetic equilibrium at the moment of the freeze out. So that means that they have to have some contact with the standard model that I'm not showing you yet, but I will soon. Yes, so at the very end, you have some comments about the detection. Yes, thanks, yes. So what I did here, remember, is change. In principle, I changed completely the mechanism. The paradigm is not annihilation into standard model, but annihilation within the dark sector. However, at the end, the dynamics is very similar because you have a particle in equilibrium that at some point goes out of equilibrium. Okay, I'm super late. I will talk now about changing this condition. In the two scenarios, I assume this hierarchy between the two breakings of the equilibrium. So first, you have breaking of kinetic equilibrium, so inelastic interaction, and then in the late universe, you have the breaking of the kinetic, so this elastic interaction, the equilibrium. Now, a comment about possible early kinetic decoupling. So what happens if I break kinetic equilibrium much before freeze out? So what happens if the two temperatures are not exactly the same? Remember that kinetic equilibrium is the one that guarantees that the temperatures are the same. So what happens if the two temperatures are different? So this is not like super weird question because after all, we know that this happened in the standard model. So instead, we know that now neutrinos are colder than photons. So if you detect the C nu B, we have some questions this morning, this is expected to be colder than the CMB, right? So we can have exactly the same, right? It's not a crazy idea to imagine that dark matter thermalizes within itself. So the dark matter has a thermal distribution, a black body distribution. So its distribution follows, is given by a temperature, but just that this temperature is different than the one of the standard model. So here I will assume that you have this hierarchy. So I'm breaking first elastic equilibrium and then inelastic. So if I get this, I expect T dark matter to be different than T standard model of T photons. Yeah? And for that, you know exactly what to do, huh? Remember? So we saw this morning several times that we expect the temperature of the standard model to go like 1 over the scale factor. Yeah, I had some question about that. And what Graciela says that we know that this has to be the case because we expect to have some conservation of entropy if the entropy is conserved. So really, it's a very clean argument. Entropy is conserved. We have adiabatic processes, and that guarantees that T goes like 1 over A. It's really conservation of entropy. So if you have, for instance, in the standard model, right? So standard model is relativistic. T goes, yes, if entropy is conserved, T goes like 1 over A. We can apply exactly the same argument, identical the same argument to dark matter. There's a little difference, is that in dark matter, we expect to be produced when it's non-relativistic. So the conservation of entropy in the dark sector will have this characteristic is that we're going from a relativistic to a non-relativistic state. And just that thing, so conservation of entropy within the dark sector, and the fact that the dark matter is going from a relativistic to a non-relativistic state gives a super nice feature, and I'm showing you here, is that we can have like an increase, a relative increase of temperature in the dark sector. And what I have to do to see that is exactly the same thing as in the standard model. A standard, for instance, to see this, or to see that neutrinos are slightly hotter colder, than photons, conservation of entropy. I can see that when dark matter becomes non-relativistic, and I will not give you your detail, just to see that when dark matter becomes non-relativistic, its temperature will not scale. Okay, let me put it like this. Like 1 over A, if dark matter is relativistic, but also scale like its mass over 3 log of A when dark matter is non-relativistic. And it's pure arguments of conservation of entropy. You can see entropy will be, when it goes non-relativistic, everything becomes Boltzmann suppressed. So you expect a logarithmic dependence on the entropy density, for instance, and therefore it has to be suppressed by a log. So here this plot is interesting. So you can see I'm showing, so that dotted line, the solid line corresponds to the evolution of the standard model temperature. Think this as a function of scale factor, right? So universe expands, temperature of the standard model goes down, right? And this dashed line corresponds to the temperature of the dark sector. So when it's relativistic, it goes like exactly 1 over A, so it's parallel. When it becomes non-relativistic, but it's in chemical equilibrium, you have a kind of increase with respect to the standard model. So it seems that the dark matter is getting hotter and hotter with respect to the standard model. Its temperature is always decreasing, right? Like this. However, with respect to the standard model is increasing. And therefore, and at some point you get out of chemical equilibrium, and therefore it cools down much faster because it's the redshift of its momentum. Right? So it's super clean argument of conservation of entropy in the visible and in the dark sector. But what you get is a super funny evolution of the dark matter temperature. And we will use that. So better not to move to chat, right?
Under this assumption, today we can assume that a little piece of the dark matter is hot now.
It's hot, you say?
Yeah, and the other and the majority of most of the dark matter is cool. So we can have both at the same time.
But let me describe what you have here. So at this point, you can see that dark matter is not really, its temperature is not increasing. It's just that it's decreasing less fast as free radiation. Yeah.
Yeah.
However, after you get like this peak, and then it goes down much faster. Okay, let me put. Okay, it was not complete here. Non-relativistic, but in chemical equilibrium. But when it's non-relativistic, okay, dark matter, non-relativistic, without chemical, it's basically 1 over A square.
Okay.
So it cools down much faster. You can see that it cools down much faster. Yes, of course, you have to, and this is basically temperatures, mean energy is like P squared, and P is 1 over A. So this cools down when it's non-relativistic and without chemical equilibrium. It's like typical energy is momentum. This is kinetic energy, P squared, so 1 over A squared. But of course, here you have to be careful with the structure formation because you want dark matter to be cold. Here typically it's not a problem, but it's something that definitely you have to keep track and to be.
Okay.
Yeah. Yes. Thanks. So all this about the evolution of the temperature, it makes particularly relevant in the case of, and there I love these names, elders. I'm talking about dark matter, and cannibals. And cannibals were not in your list, so at least something. Because the idea is exactly the same, right? So if I want to compute this final abundance, which I say that it's typically the dark matter abundance at the moment of the freeze out, and remember that was the number density of dark matter over the entropy density by construction. But here the temperatures could be different. So I have to put here the temperature of the dark matter, the prime is the dark matter, and the temperature of the freeze out of the standard model. So here I have to do basically the same idea that I have done for WIMPs, for SIMPs, just take into account that the two sectors could have a different temperature. And I can compute this. So I will not write the expression, but it's typical. I mean, what you have to do is normal thermodynamics in an expanding universe. So you know what's the expression for the entropy density. You take the Colban-Turner, for instance. The number density, you have different temperatures, but you know how temperatures evolve. So you can evolve that numerically with a Boltzmann equation for the difference of temperature, but you can also do it analytically. And just want to give you 2 examples. So this Y0, so I have like a couple of minutes, right? Like 15. And I have, remember WIMPs. So for WIMPs, this was for WIMPs, the important thing that only depends of X freeze out. Here I will have one expression that goes like okay, let me do this. I'm not writing the full expression, just 2 limits. One limit, which is the elder solution, and one limit, which is called the cannibal solution. Here, I'm just assuming this hierarchy. So I want the freeze out, the chemical freeze out, to be non-relativistic because I want cold dark matter. So I always want to have this hierarchy. But what I'm playing is at which point, when is this guy decoupling? So kinetic interactions, so elastic interactions. They could decouple when dark matter is relativistic or when dark matter is non-relativistic. So this is the possible hierarchies. So if this kinetic decoupling happens at the very late time, is either a WIMP or a SIMP. If it happens between the mass and T freeze out, is what I call an elder. And if it happens when dark matter is relativistic, I will call it a cannibal. So I'm giving you the two expressions for the final Redick abundance. In the case of cannibals, it will only depend on the freeze out temperature, like in the case of WIMPs, right? Only of X freeze out. However, in the kind of elders, it will have a strong dependence on xk. This is xk. Here, there's a power law, but also in the exponential. So that means that for cannibals, what I'm having is like the full increase of temperature. However, in the case of elders, I can play with the moment at which it goes out of kinetic decoupling. So I'm kind of playing with the relative increase of temperature, right? So maximal increase and partial, yes. Yes, good. So I put prime. So for me, yes, I forgot to say that. X prime freeze out. Prime is with respect to the dark matter. So it's T freeze out, but prime, right? And K doesn't matter, but because remember TK, so by definition, Tk is always the same as T prime K. It has to be the same because it's the last moment at which this equality is guaranteed, right? So yes, and okay, sorry. I'm showing you here, okay, first, a plot of the evolution of the dark matter abundance. It's very similar to the case of WIMPs, so it's basically the same plot. So this yield Y as a function of X, so 1 over the temperature of the standard model. So the blue dotted line corresponds to the equilibrium with respect to the equilibrium with the temperature of the standard model. However, the dark matter has another temperature, and this red dashed line here corresponds to the equilibrium with respect to its temperature, so it makes sense. So dark matter is in equilibrium, but the equilibrium with its temperature, right? Not with the temperature of the standard model. So it's normal of dark matter tracking the equilibrium, but the equilibrium again with respect to its temperature, which is higher. So you have a higher occupation number, higher abundance with respect to the standard model, with the temperature of the standard model. And at some points, okay, you have the decoupling more or less here, so the temperatures are not the same. And here you have the freeze out, so the chemical freeze out, right? So you can see here the same, just zooming on this box here. So here you can see the dark matter reaches a plateau because it's not in chemical equilibrium anymore. And here is basically the same information I gave you. So I'm having the freeze out, the chemical freeze out, as a function of the kinetic freeze out for the four mechanisms that I discussed previously: WIMPs, SIMPs, elders, and cannibals. So remember, WIMPs, for instance, is this part, this solution. When it's vertical, that means that it's like here. It only depends on X freeze out. It's independent on XK. That means that it has to be vertical. And for instance, okay, these four lines correspond to different masses: 1 TeV, 1 GeV, MEV, and KV. This is very light. I just put it for complementarity, just to see the evolution. But for instance, for MEV to TeV, you need a WIMP that decouples when X is like 20 or so as expected. At some point, you reach the elder branch. So it depends on both parameters. But of course, it depends on the kinetic freeze out is much more important. That's why it's kind of horizontal, not completely, but kind of. And then at some point, you can reach, if dark matter mass is very light, to the cannibal mechanism, which, and again, you recover an dependence only on X prime freeze out. Yes? A couple of minutes more, sorry. So here in this kind of scenarios, both on elder and cannibals, also what I have in mind is also this kind of reactions. So 3-2 or 4-2, just to understand, again, this increase of temperature here. You can imagine that when you have this increase of temperature, it's in the case where you're going, for instance, from 3-2, for example, right? So here you have 3-2, what you're trading mass into kinetic energy, right? So you can imagine you have 3 non-relativistic dark matter particles that are annihilating into 2 dark matter particles, but with a high kinetic energy, so relativistic. So you can understand this increase of temperature in these two senses. At the end is exactly the same, right? Either conservation of entropy or what they call cannibalization, right? Therefore, cannibal dark matter. So your dark matter is like eating itself, and so trading mass into kinetic energy, and therefore its temperature has to go up. So cannibalization, 3 non-relativistic dark matter into 2 relativistic, increase of a typical kinetic energy, and therefore the velocity. So yeah, that's basically, okay, I can do exactly the same here. So here is like model particle physics independent in the sense that I'm not fixing coupling. So I mean, here it is completely valid, right? So I don't have to fix a particular model. However, if I go to a particular model, I can think about typical couplings. And here, for instance, it's basically the same information, but just projecting a more particle physics friendly model. So here I have a coupling, so I'm assuming just contact interactions, right? Very simplistic scenario. So epsilon here parameterize the coupling with the standard model, while y here parameterize, like here, the interaction within the dark sector. So you can see the three solutions. So WIMP, that will depend on the interaction with the standard model. Then you have the SIMP branch and the elder branch, and at some point they could eventually go to the cannibal. And just, I mean, the last 10 seconds, of course, if in all these scenarios, I want to have a kinetic equilibrium. So you have to have some connection with the standard model, just to answer your question. So that means that it's possible to look at this. I mean, if I have quartic interaction or interaction within the dark sector, I can also use, for instance, information from the bullet cluster that we have Graciela discussed this today. So you can have bound for the total amount of dark matter self-interaction from the bullet cluster. This is the same plot I showed you before. And for instance, all this region is ruled out because you have way too much self-interactions. But if you go to a particular model, for instance, here, I can look for this guy with the direct detection. For instance, if you have interaction not with nucleons, but with electrons, because remember, all these elder and cannibals and SIMs require light dark matter, light in the MEV ballpark. And I think you will see next week that if you have, if you're in this ballpark, interaction with electrons, direct detection with electrons is a particularly well-motivated target instead that of with nuclei. And here just I'm showing you some numbers, right, and projections. So regions have null plot excluded already with Xenon 110, and this projection to test like this natural parameter space of light WIMPs, SIMs, and elders. So elders is this line, WIMP is this line, and all these between could be the SIMP paradigm for one particular model. But of course, if I change model, for instance, in the case where I have mediation with a dark photon, I can use all this mechanism and translate all the bounds coming from dark photons to this scenario. So yeah, sorry, I have been super fast. Yeah, but that's all what I wanted to tell you today.
Thank you. So now we will have a question session, but just before we go with the questions, I would like to remind you about the sign-up sheet, presence sheet. So it seems it's not efficiently circulating among people. Does someone have the sheet right now, presence sheet? Did it got lost along the way? Afternoon presence sheet. Okay, so please circulate it around. If you didn't sign yet, do so. You have 30 minutes for that, right? So, okay, so apparently this is not circulating easily. So we'll make it circulate again. We will leave it at 5 minutes within the talks. But please be sure to sign. Like now everyone is supposed to be here, right? So everyone is aware. If someone goes home not signing it, don't try to sign tomorrow. You were not here, right? So if you didn't sign, complain. It didn't get to you, complain. Same tomorrow and every day. If the sheet doesn't get to you, complain. Just don't sign up, okay? Because we need to know that people are here. Of course, you know, some people are getting funding. This is public money, so you want to be sure that the taxpayers are giving money for something. Also, as you know, there is a lot of pressure to participate in the experiments, so you want to be sure that people that are participating in the experiments are attending the talks. So sorry about that. I know it's annoying, but, well, we think we need that. Anyway, so, and regarding the posters,